I'm going to welcome Saul for X to the stage.
Good morning, everyone. My name is Kate Ahira. I'm the program lead for Solve for X. And before we kick off the presentations, I just wanted to give you a bit of context of where this has all come from. When Larry and Sergey set up Google X, their vision was to dedicate some of Google's resources to developing a skunkworks-like lab that focused exclusively on technology moonshots. But practically speaking, what does this mean? For us, technology moonshots are projects or ideas that address a global problem that has the potential to impact millions, if not billions of people, through a radical solution that may sound like science fiction today, but could become the everyday in 5 to 10 years' time. And these solutions are based on some breakthrough in science or technology that gives us the confidence that even though it might be incredibly hard, it is possible. By way of example, take the self-driving car. Every year, millions of lives are lost in car accidents. What if we could avoid all these deaths by developing cars that could drive themselves and react to what they perceive around them? This is becoming more and more of a reality through advanced mapping and live sensor data. Or take Project Root. 2/3 of the world doesn't have access to the internet. What if we could quickly fix that by sending up a network of stratospheric balloons traveling at the edge of space, which provide connectivity to the most rural and remote parts of the Earth? At Google X, we know we stand on the shoulder of giants, the likes of the Nikola Teslas and the Marie Curie's that came before us. And we also know that we're not alone today. There are hundreds of individuals and teams throughout the world working on technology moonshots, and we're united in our passion to make the world a radically better place. Solve for X was set up to help jumpstart a wider moonshot ecosystem, where as a community, we get behind accelerating progress in achieving these types of audacious proposals. I'm going to share a quick video from those who can say it better than me, and then we'll kick off the presentations.
The actual moonshot is wonderful, inspirational, poetic, beautiful, involved great technical challenges, genuine heroism. It brought the world together. But think about the Polynesian islander on a dugout canoe, deciding one day they were going to go that way. No one had ever been that way before. No one even knew there was anything that way before. It was amazing, and it changed the world.
People can set their minds to magical, seemingly impossible ideas, and then through science and technology, bring them to reality. And that then sets other people on fire, that other things that look impossible might be accomplishable.
Galileo is such a hero, in thinking big, and what he represents to me is both curiosity and wonder that humanity had, that he had that pushed him and drove himself to invent and work on the first telescopes that allowed us to see the moon, and here we are.
These aviation pioneers were figuring it out as they went. No one really knew how to build an airplane, right? No one knew how to fly an airplane. It was amazing and crazy and wonderful, and they wanted to explore.
Many years ago, the great British explorer George Mallard, who was to die on Mount Everest, was asked why did he want to climb it. He said because it is there.
There's so many challenges in the world, and you can feel daunted by that, and repressed by that, or you kind of say, how might we think differently about this?
Everyone else in the world is working on the next 10%. If you can be the one that delivers that 10 times improvement, you have a chance to really change things.
If you want cars to run at 50 miles per gallon, fine, you could retool your car. But if I tell you it has to run on a gallon of gas for 500 miles, you have to start over.
You need a lot of courage in this work, and you need a lot of persistence. And one of the things that's really critical is not only having courage to keep trying every day or thinking big, even if you don't really 100% believe it's possible, like you might think, this might be possible, have the courage to try. That's how the greatest things have happened.
You don't spend your time being bothered that you can't teleport from here to Japan, because there's a part of you that thinks it's impossible. Moonshot thinking is choosing to be bothered by that.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Humanity's progress has been been a series of amazing, audacious things, something very small and personal to very big and grand. And we are a species of moonshots. And to me, that's like a really amazing poetic inspiration.
I think our ambitions are a glass ceiling on what we can accomplish.
When you find your passion, you're unstoppable. You can make amazing things happen. It's been true throughout history.
I believe in the human spirit, and I believe that there are always going to be crazy people who get out of bed one morning and say, you know what? I think I can go to space alone. I most would do it. But I think that if we become afraid to take these great big risks, we stop inspiring people. We stop achieving things. And the biggest nightmare scenario is that we won't have what it takes to solve the really big challenges.
When Kennedy said that we would put man on the moon, it's about the fact that he said, we don't know how to do this yet, and we're going to do it anyway. And that sends chills up everybody's spine. Because if that happens, what could we do?
So we're privileged to have three speakers who are going to share their moonshot proposals with us this morning. I will introduce each of them in turn. This will be followed by a brainstorming session where we invite you to spend some time working together to really build on what you hear today and report back to them any ideas that you might have to really progress and accelerate the work that they're trying to do. So first up, we've got, did we Rachel? Did you go first? Where's Nikita? Where's his brain first? So first up, we've got Bruce Shield, who is the co-founder of Helical Robotics. His mission is to change the face of industry by mitigating risk and increasing profitability through the use of robotic solutions. So if you could please welcome me in giving a big round of applause to Bruce.
Before we get started, I'd like to thank my brother, the other co-founder of Helical Robotics, for putting in all the time to create all of these crazy things that I've come up with in my head. But and today we're going to talk about infrastructure and how we can make infrastructure better, faster, and cheaper through the use of mobile robotics. The world is getting smaller every day. There's more people. There's more cities. Kind of the third world is becoming the first world at a crazy rate. To put it in some form of context, the American Society of Civil Engineers every 4 years takes a look at the states and says, what would it cost us to put all of our modern infrastructure up to spec? And that number right now is $3.6 trillion US. And the States is just a small fraction of the world infrastructure. Now, that lofty goal sounds good, but that's not where it started, right? I found my exit bar, and let me set the stage for you. So we're out in the pub having some cocktails, and somebody stands up and says, I've never done your job before a day in my life, but let me tell you how to do it. And that night I was the guy standing up. And the job was inspection and maintenance of wind turbine blades. And this is my bed. So on the right-hand side is traditional wind blade inspection. All right, there's a guy hanging from a rope. He's about 300 feet off the ground. And he's just looking at the blades, trying to find problems. On the left-hand side is one of our robots, and it climbs a tower and uses a high-end camera to do that same sort of inspection. So it dramatically reduces the cost and the risk and all the things that go along with it. So how do the robotics solve for X, right? This is the only equation in the whole thing, but I think that this is a very important equation. It's called the iron triangle. And what it says is that for any one thing, you can have it good, fast, or cheap. Pick any two. And I fight with everybody in my company about this every day, because I want it all, and I want it now. So through the use of any disruptive technology, so for today's discussion, it's mobile robotics, I think it's possible to do that for a short while. This is an example of that. So on this side is a automotive assembly plant, 1928. Right? There's lots of people. They're building cars in days and weeks. On the other side is a modern assembly line. So that's all nifty factory automation. And that builds a car in hours or less with very few people. So what we're trying to do is build a mobile robotics platform that can go out and do all that same sort of stuff on big infrastructure. So when we started out, right, we're smart guys, we're like, this is a complex problem, so the complex solution is up top. It wraps around things, and it was very, very big and bulky. And one morning in the shower, I thought, gosh, you know, I'm climbing on a metal set. If we put some magnets on it, then very quickly we could climb a tower with a small machine that was the right cost, right? Instead of having a $200,000 solution for a $5,000 problem, we're more in the right ballpark. So that's kind of where it went through the climb. This is a quick video of kind of where we started with the climbing robots. This is our first prototype, and as you can see, it's very stable, climbs around, and you know, can change direction with the use of mounting wheels. And then, as we refine that, we simplify it. How do we make it better, faster, and cheaper ourselves? So this is our current, one of our current off-the-shelf models, and the point is to put on it whatever you want to put on it. So cameras, robotic arms, sensors, any of that stuff. And to have a mobile platform that's versatile enough that you can put different stuff on the same platform. So it's, you know, easier to integrate new technology. So this is delivering rope rescue equipment to the top of a wind turbine. We had a company that said if there was a turbine on fire, we'd like to rescue people. So this is something that we put together very quickly to save them. And then it's not just for wind turbines, it also works on other surfaces. So here it is on the side of the ship. All right, so our goal is to get a robot for everyone, right? Different robots doing different things. So ground-based and flying robots, that's not what we do, but that's what other people in mobile robotics do. And that's one of our biggest challenges, is that it can do lots of stuff, but I don't want to have to build hundreds or thousands of prototypes to prove out what it can do. So how do we figure out how to show the technology in conception to industry so that they can do with it what they want? Because we're not experts on everything, right? We build robots. So one of the big breakthroughs that allow us to do this today when it could have been done, 10 years ago. And they're the standard things, right? The small integrated circuit board in your phone is more computing power than probably what took the astronauts to the moon in '69. And small sensors and small batteries, because if we want to power the thing, it has to be lightweight, it has to be compact, and things like LiPo batteries are making that possible. The last one is machine vision. Now that's a picture of what the Google car sees when it drives up and down the street. So being able to give your automation that level of understanding at a reasonable cost is really driving the market. Now, what's cool about Solve4X, I think, is that it allows us all to see what kind of the crazy, off-the-shelf, out-of-the-world stuff that everybody's doing. And this is a company called RE.WORK that I saw in one of the other Solve4X presentations. Saul Griffith is working on something called soft robotics. And what soft robotics is the entire thing is sewn together, and it uses air and fabric to create a mobile arm. And this proves that Saul is smarter than me. I went to the bar and decided to build a robot, and he built himself a robot so he wouldn't have to go to the bar anymore. And it's very cool because it's lightweight, and it will eventually, hopefully, partner up with a technology like ours so that you could climb out on a bridge or a building or a pipeline or a wind tower and have a lightweight robotic arm that can move other sensors or more robust equipment. So, as this whole thing comes together, right, there's all sorts of these companies that are building various technologies. Google with their self-driving car, but it could easily become a bulldozer or a tractor or anything else that would automate lots of infrastructure. An example of where we might be able to help is doing work on bridges and roads, right? So you've got a car that's out there driving itself. So what if it can speak with and talk to all of the construction workers, right? We're able to take a basic platform and give it the mobility and the intelligence to go out and do lots of work and make things more efficient. And kind of as all that comes to fruition, you wind up with a paradigm shift. And the paradigm shift is that not only do you construct or maintain and operate the infrastructure, but you will start to design the infrastructure so that it can be built by mobile robotics. So this is a pipeline that I had our guys put together, and it's being completely constructed autonomously. So, imagine being able to run a pipeline across the desert, and there's no people out there. It's just it's bending itself up and building itself, and at the end of the day, it's very efficient. And that brings me to the other big issue that we have, is that when people talk about paradigm shift, they're talking about what an old mentor of mine told me was called fuss and bother, right? So we all work 40 hours a week or less, right? Go in, 8, go home at 5. So you see something cool, and you're already taxed out, you're tapped out, your day is full. But to do something like this takes lots of fuss, lots of time, and the bother to follow through with it. So how do we get people to say it's worth the time to be disruptive? And I think as the technology proves out that in a way it does it on its own, but you still need buy-in. Excuse me. So in closing, I guess I'd like to say, the next time you're at the pub trying to solve the world's problems, be careful. You might find yourself up a pole without a ladder. Thank you.
Thank you, Bruce. Next we have Rachel Armstrong. So Rachel Armstrong is the co-director of the Advanced Virtual and Technical Research Group at the University of Greenwich. She'll be exploring the possibility of transforming our cities into fertile synthetic soil producing systems. Please join me in welcoming Rachel.
The processes that underpin human development are damaging to our environment to a point where our ability to meet our needs and that of future generations is being compromised. Effectively, we have a monoculture of technology which has facilitated our rapid expansion. But at the same time, it's contributed to a change in our planetary metabolism by unlocking stored carbon dioxide from fossil reserves. Now, these processes are contributing to changes on everyday experiences with phenomena such as climate change, global warming, sea level rises, acid seas, fascination of our oceans, and a loss of biodiversity. By diversifying the available number of technological species in terms of their metabolic types, we might use a broader range of substances and produce a more diverse portfolio of waste products. Such technologies may become hubs for the exchange and flow of materials, where the products of one system become the raw materials for the next. And potentially, we could develop technological solutions that are as diverse as life itself. And these technologies may work alongside our mechanical technologies and mitigate some of their chemical impacts before they reach destabilizing concentrations. My research examines the potential of natural computing as an alternative to machines, a different kind of production platform. And the term is inspired by Alan Turing's interest in the computational powers of nature. And these do not work in the same ways as machines. Now, whilst machines are made up of object hierarchies that assume the world is effectively at equilibrium, natural computers exist spontaneously in non-equilibrium systems, such as galaxies, tornadoes, and snowflakes. They may be found in interfaces where molecules with different properties butt up against each other. Nature itself is, of course, a non-equilibrium system, and therefore natural computing shares a common language with natural processes that are based in the hardware and software of physics and chemistry. Now, the dynamic qualities of natural computers may be harnessed through a range of different techniques by changing their internal and external conditions, so that these dynamic materials may be harnessed to perform useful work. Now, my work is centred on the oil-water interface. I use amplifiers, which are a particular kind of molecule that is strongly attracted to water on one hand and completely repelled by it on the other. And this means when you have molecules that are all lined up and they're coming into contact with water, they form an interface that's full of energy. You do not need to provide external energy to the system. So consequently, even small molecular disturbances produce huge amounts of movement. So that is why water and oil immediately, spontaneously self-assemble into droplet formations. But we can manipulate these molecular scale interactions using soft forms of control to produce microstructures such as crystals, as in this picture here. And they may also be spatially directed. Now, I developed a series of chemical organs for these paleozoic ground installations for the Venice Architecture Biennale in 2010, using the principle of dynamic interfaces to produce sculptural centimetre-scale objects, and these would change presence change colour in the presence of carbon dioxide, which was breathed out by gathering visitors. And notionally, this installation can be thought of as smelling or tasting its audiences, because it is responding to chemical signals in a very similar way that our own sensory systems do. Now, this is an incredibly simple approach. Nature provides many dynamic interfaces that process matter, for example, in cell membranes, at the seashore, and in deep sea vents. Now, perhaps the most prolific interfaces are essential for life on Earth, and they are our soils. Now, these are varied, geological scale living bodies that entangle chemical and biological interfaces, and they can be regarded as a kind of technology where they're manipulated to perform useful work. The example I'd like to give you is that Frank Rube and his colleagues at the University of Adelaide recently showed that gold nuggets are often the creations of bacterial biofilms in soil. So potentially then, it is possible to construct a soil that can extract gold. Now, my research was not aimed at the Midas touch, but to act as a site for technological convergence, where chemistry, biology, nanotechnology, and information technology may meet together to create organs within, for example, our buildings that process their surroundings. For example, synthetic soil systems may remove environmental toxins such as lead, purify water, provide heat and insulation, and even food. Some of these technologies already exist, such as anaerobic digesters, but we can do better. We can design much more creatively with these kinds of systems. So we may think of our buildings as having organs that can be linked together as physiologies that can produce discrete, locally shaped, geographically varied substances and metabolisms within our cities, not as a metaphorical rhetoric, but as a literal way of transforming not only our environment, but also our own lives, so that we become producers, not just consumers of our environment. And ultimately, this will help us have cleaner, more fertile, and livable urban environments over the long scale. Now, the challenges of realising these goals are really firstly conceptual, as our buildings have historically been conceived as inert barriers between us and our environment. And in order for us to live in a condition of natural abundance, we need to make sure that our interfaces are actually synthetic ones and not simply a big membrane that exists between us and the natural world. So I think there's one other thing that the first thing that I would change within our living spaces is our infrastructure. Our buildings are designed to be dry. Life is wet. I would suggest that instead of our buildings being drains, that there would be circulations where molecules can be transported and reassimilated within our homes, within our kitchens, within our bathrooms, so that we're actually living together with post-natural fabrics where natural and synthetic systems are seamlessly entangled. Thank you.
Thank you, Rachel. And last we have Skylar Tibbetts. Skylar is the director of the Self-Assembly Lab at MIT, and you'll be exploring how we can revolutionize the assembly of our physical world through the phenomena of self-assembly and programming matter. Please join me in welcoming Skylar.
Okay, so what I want to talk about today is what has happened with the introduction of computation of software and the introduction of fabrication. If we look at what it has given us, it's really amazing. On the one hand, it's given us this ability to design complex things that we could have never designed before, massive iteration, analysis, and open up this huge design space. On the other hand, it's given us the ability to make things that we've never been able to make before. This DIY revolution in digital fabrication is becoming more and more ubiquitous. So this is just really amazing on the design and fabrication side. But if you look at what it hasn't given us, one thing is a new perspective on the assembly side. Assembly is predominantly unchanged by this digital fabrication and computation revolution. We're still assembling things predominantly by hand, or at least in brute force techniques, where parts are forced together with excessive energy, labor, etc. This is me assembling a prototype for 6 hours straight. You can see it's not the most fun. It takes a while. So the point is, if we look at industrial applications of construction, manufacturing, and assembly, there's massive amounts of energy that goes into this. Many people, man-hours, errors, dangerous conditions, low wages, etc. There's this huge opportunity for industrial assembly to be revolutionized like computation manufacturing now. And so if we look at another scale, not the industrial sector now, but if we look at synthetic biology, chemistry, and material science, there's a revolution happening. We're able to program physical and biological materials to change shape, change properties, compute, and build themselves. And so this is really a paradigm shift because it doesn't mean that we're forcing things together in traditional ways of assembly, but rather we're embedding information in materials and we're letting the materials assemble themselves, error correct, make decisions, as we previously heard, compute, and many other things. So there's really a new opportunity. And so what I'd like to propose is that we should transition from the mindset of only automation to the mindset of smarter materials and self-assembly. And that doesn't mean get rid of smart machines. We know we need smart machines. We know we need smart people. But we're also arguing that we need smarter materials that can make decisions and that they can work together collaboratively. That materials offer something, machines and people offer other things. So self-assembly is defined as a process by which disordered parts build an ordered structure through only local interaction. That means the parts come together on their own, no human interaction, no external influence. So the vision is really that we can transition from a world that looks something like this, where we have lots and lots of parts that come together in lots of complex ways, complex processes, instructions, etc., into a world that looks much more like products that are responding to the user, products that are adapting to the environment, smarter materials that are responding, adapting, containing information and decision-making, manufacturing processes where the materials are assembling themselves, they're error-correcting, communicating with local neighbors, energy sources. Shipping looks more like shipping flat materials that pop into place without assembly instructions. And disassembly is completely changed. This might be more influential than all the rest that I talked about. You could look at disassembly on one hand and say, first of all, there's no trash anymore, that everything can be broken down to fundamental ingredients and built back up. You could look at it and say, no, there is failure, but parts can repair themselves. Or you could look at it and say, yes, there's failure, but everything self-sorts, so there's pure recyclability. So there's this huge space in the industrial sector of products, manufacturing, construction, that could be completely revolutionized if we have smarter materials. So what are the ingredients for this technology? There's three main ingredients for self-assembly. The one on the upper left-hand corner is components. These are materials and geometry. We need to be highly tuned into the shape and the material property available. And then that needs to be designed around the interactions. So how do these parts come together? How do they change state from one state to another? How do they error correct? And then how do they link with energy? What's the energy that gets them excited? What's the energy that gets them from point A to point B? And how do we design around passive energies? So not just fuel and current, but heat, shaking, gravity, pneumatics, fluids, all of these abundant energy sources that are primarily cheap and around us everywhere that we could use to excite these systems to become self-assembled. I'm going to show you a number of projects now that try to demonstrate some of these capabilities. These come from my lab at MIT, the self-assembly lab. This first one is a collaboration with Arthur Olson, molecular biologist. We built 500 of these glass flasks. In each flask is a different molecular structure. It's a macro scale version. You shake it hard and it breaks apart, and then you shake it randomly but a bit softer, and the parts come together and they self-assemble back into the final structure. So for me, this demonstrates that random, noisy energy can build non-random, precise structures. So the user doesn't know anything about the parts, they're giving noisy energy, and the parts are building it for you. We also demonstrated self-sorting. We dump a bunch of black and yellow parts, we shake it randomly, and they always self-sort into fully black, fully yellow, so they can self-select. At TED 2012, Arthur Olson and I did a much larger scale one to demonstrate scalability. We made these furniture scale objects. Again, with 12 components, this was looking at the poliovirus. And there's a large rotating chamber. The reason we call it the self-assembly line is because we want to switch or flip the perspective of the assembly line. In this case, the user comes up and they add energy. They don't even know what they're making. They don't know how they're making it. But they're just giving energy to the system. And they start to build an intuition. How much energy do I need to give? How much is too much? How much is not enough? And the parts have all the instructions in them. The parts have all the capabilities to assemble this final furniture piece. So the users are interacting and understanding this non-intuitive process. And for me, that's one of the biggest takeaways from these projects is that they become demonstrations of another possibility for how things can come together. A possibility that's not necessarily intuitive and not necessarily thought of in our human scale domain. Self-assembly is not something we normally interact with. But once you see this, it quickly becomes intuitive. It makes sense that it can go together. And therefore, we can then turn the corner and start to use it for other processes. The last one I'll show you in the self-assembly category is a project we recently did in New York called fluid crystallization. We're looking at material phase change and intra-molecular bonding. The idea was, could we design self-organizing systems that could change phases? We had 350 of these neutrally buoyant spheres. So you'll see here, you drop a sphere in, and it's neutrally buoyant, so it moves in all three dimensions effortlessly. We have these pumps in the back, and we can program the turbulence in the water. So we can increase, we can have oscillations, chaotic patterns, random patterns, regular patterns. And so what happens is that you have these freely moving elements, they start connecting to one another, and they're building systems. And they're building either regular or irregular systems, locally and globally. So what happens is in the middle, they start to break apart, because that's where the greatest amount of turbulence is from those pumps. And on the side, they start to assemble. And if they assemble as one solid piece, let's say in a regular lattice, that might be a crystalline solid, or an irregular lattice, still a solid object. If they're kind of fluid in the middle, that becomes a liquid. If they're more gaseous and they're moving around, that's obviously a gas state. And so it's more a demonstration that self-assembly or self-organization doesn't necessarily need to lead to the same output, but rather we can look at how behaviors change of a larger, more complex system. And locally, you'll see here there's a pentagon, you'll see other kind of hexagons, pentagons, local structures that are very deterministic. They happen over and over and over. But the global behavior is much more complex. It's more about the energy in the system, the entropy of the system, how many parts are there, and what their behaviors become. And so you can guide them towards certain behaviors, but the final structure is not necessarily only a dodecahedron or only a precise shape, as seen in the previous ones. The last project that I'll show is focusing more on programmable materials. It's a project with Stratasys. It's called 4D printing. The idea was that we take 3D printing and we take smart materials and we combine them together. The reason we called it 4D is because we wanted to add the element of time. That when you print something, it's not finished, but rather there's this element that it changes over time. And so we wanted to heighten that. This is essentially like printing smart materials or printing transformers, if you want to look at it in that perspective. We've used the multi-material convex printer, so we deposit two materials at the same time. This is a time lapse showing that. One of the materials is the black material that you're seeing here. It's a rigid plastic. The idea is that that becomes the structure, the angles, the backbone, the limiters. That's all of the information. And then another material you'll see in a second is a white material that expands 150% in water. And so when this is dipped in water, the letters fold, or the strand folds into the letters MIT. And then this strand dipped in water folds completely on its own. There's no human interaction here. It folds into a rigid three-dimensional cube. And so the program was embedded in the rigid material, and the energy was embedded in the expanding white material. So we can combine those two to build precise structures. Here's a two-dimensional surface. So this is demonstrating that we can do one-dimensional strands, we can do two-dimensional, you can do three-dimensional objects. You can print anything that you want to print, but you have the added capability that it's going to transform. It's going to have some sensor capability. The environment is changing, it meets water, and it transforms into something highly precise. So you could use these as sensors and actuators. Essentially, it's material computing. There's no external electromechanical devices or traditional notions of robots, but rather it's materials themselves that have that capability. That's folding into a surface cube. And then the last demonstration of this project, this is a 50-foot strand. We rented out the Olympic pool at MIT. We dipped this 50-foot strand into the water. Over the course of an hour, it transformed 75 times its linear length. So it demonstrates that first, this is scalable. We can build really large-scale structures. And in many ways, this is still unfinished work, and we're trying to push this forward. But it also demonstrates, going back to the idea of changing the intuition, that maybe these systems could be used to study protein folding or much larger, non-intuitive scenarios in physical, tangible medium. And that we can use these programmable materials or self-assembly systems to really change our perspective of how we make things and how things transform at the human scale. So I'd like to leave you with a quote which I think sums up the challenge of how we can really revolutionize the assembly at the industrial scale. Can we design material parts with enough information and decision-making that they can assemble themselves and adapt independently to internal and external forces? Thanks so much.
Thank you, Skylar. Those were three fantastic presentations. Can we give them all a round of applause? Next, I'm going to introduce a colleague of mine, Krishna Shah. She is the Strategic Partnerships Lead for Solve4X. She's going to walk you through the next part of this session and moderate how we're going to break into groups and brainstorm and report back.
Thank you so much, Kate. How's everyone doing? Good morning. Still awake to do these presentations? Maybe. Thank you so much, Bruce, Skylar, and Rachel, for being here. I think the great part about conferences like this is it gathers great minds in a room. And each of you have heard three fantastic moonshots. They're all breakthrough technologies, but they're all still ways away from being a radical solution that is globalized and that we see everywhere. And so I think everyone in this room is uniquely positioned, either because of your experiences, your ideas, your connections, your knowledge, to help push forward a moonshot. And a famous quote is, "It takes a village to raise a child," but it actually takes a village to help push forward a moonshot. And so with all of you in this room today, instead of having you listen to the presentations, we actually want you to take an active role in helping to push forward these moonshots. So what we're going to do is we're going to gather into groups of about 6 people. And I see that some tables don't quite have 6 people at them. So in a second here, when we break out, please try to form slightly bigger groups, and I think towards the back is fine. But basically what we're going to do is we borrowed this idea from improv comedy, and it's called 2/3 yes and, 1/3 yes but. And what that means is in your groups, we would love for you to either pick one of these presentations, or you can talk about all 3. Obviously there's limited time. But what we want you to do is spend 2/3 of your time discussing anything that you possibly can to help push forward the moonshot. Ideas you have, thoughts you have, maybe where they can expand next. And then for 1/3 of the time, it's good to be grounded in reality. So we want you to propose solutions to some of the roadblocks and challenges that they presented, or maybe new roadblocks and challenges that you might have thought of. And so what we're going to do is break out right now. We'll give you a 5-minute warning, and really you can talk about anything that you'd like. We'll give you a 5-minute warning, and then right after that, we'll have one person from the group come up and present your ideas from the group to the larger group. So without further ado, why don't we get into those groups, and Chris and I will be walking around to help facilitate a little bit, but you guys are on your own. And it's going to be cool what comes out of this. It always is, every single time. So, alright, without further ado, let's start out. Hi everyone. Nice to have your attention. We have our first group already. So, in the meantime, you guys can get started, but we have Christina and Elise up to present which topic you guys want. Self-assembly.
Hello everybody, I'm just going to explain a little bit about why we chose self-assembly. We were all excited. Actually, all three of those topics were mind-blowing, but with this particular one, I think we could immediately see applications. So a few of the reasons why we chose this was the fact that you can have random and maybe potentially unexpected results with this technology. You appeal to some of the sense of chaos we like. The fact that it's intuitive and the user doesn't actually need much information in order to create something, and a lot of the programming and data is upfront, so it really forces us to think about a value chain where the design is upfront rather than the customization at the end. I think it's very efficient. And I think the other appealing concept is that it frees human time and risk, because a lot of the assembly that we were thinking about happens in places where humans may be at risk. And it has interesting crossover perhaps with Skylar's work and Rachel's work, we thought, and even I think Bruce's work could really cross over from a lot of the yes and concepts we were thinking of. So Chris is going to discuss those in a little more detail.
Hi everyone. So we spent quite a bit of time thinking about where the real value lies in self-assembly. And we decided that it was probably in 4 or 5 different areas. Areas where the assembly time was very valuable. You were saving that time by shifting it to earlier in the supply chain. So you're shifting essentially assembly time to design time. Where might that be valuable? Well, it might be valuable in some consumer applications. So we all hate assembling our IKEA flat pack wardrobes, but if you can just take it into the garden, hose it down or something, then I think people will be willing to pay for that. It also might be valuable in applications where it's difficult to put a person. So we were thinking maybe underwater applications, space applications, things where actually putting someone in place to assemble something is quite dangerous and expensive. We were also thinking about areas where you have a particularly complex form that requires very detailed instructions, and you may not rely on the person who's doing the assembly to follow those instructions or to understand the instructions. And hence that led to applications we're thinking of maybe where you have large illiteracy or people who essentially didn't have the technical knowledge to assemble something. That led us to thinking about things like very large-scale infrastructure developments in the developing world, self-assembly bridges, things like that. We also were thinking about where there might be risk associated with incorrect assembly. Again, if you don't have someone on site with the technical capability to oversee something and say is it being assembled correctly, then there might be particular value in putting more effort into the sort of upstream design stage and having the self-assembly. And the other application area we were thinking of was where there was a large cost associated with delivering the bulk items. So again, going back to the kind of flat pack type application. The very final area we thought of was customization. So at the moment, could there be applications where you want essentially something to complete a little bit when you've got it? So maybe white goods, you kind of get your fridge freezer, it slides into place, and you just want to kind of expand or contract a little bit to kind of make your kitchen a little bit neater. Finally, we spent a little bit of time talking about disassembly and trying to identify areas where there's a lot of value in being able to take something after the end of life to a way you can reconfigure it. So in addition to kind of spraying your IKEA furniture with water to make it assemble, you spray it with something else to make it disassemble and easier to take to the tip or reconfigure.
where do you have an idea of your endpoint of a product or the components of it before it was built? And I think that's pretty cool. So I think we're running out of time, so I think I'm going to just rush through the last few in terms of what would the implications of this be, and I'm sure Scott's got opinions on this. The fact is that if you have this kind of possibility, you're talking about an impact on the human value and skill sets that you'd actually need for a product to be made in the world, any functional products. And what does that mean for the skill sets people need? What does that mean for jobs? What does that mean for transport, logistics, and shipping? So we're thinking it would have quite fundamental shifts, and obviously that would be over time. But I think I'm going to just stop there because we're running out of time. Thank you.
Thank you guys. Next we have Paul, and if you guys could just keep it to a couple of minutes as we've got quite a few tables to get through.
Hi, I'm representing this table just here. Delegated to me. I don't know about anyone else, but actually I quite like making this presentation. It's quite satisfying. So I don't want this build itself. I quite missing it. I like going and buy those extra screws that you're missing. Anyway, we split this into two slides, very much around self-assembly as well. It's obviously the human calculating one, both the human and the environmental issues. So in terms of, I think the sort of human side, our first thought was around the real value of where there's so much present. So around the area of surgery, where we could do something on a very small scale, add something into the human body, which would then formulate a shape which would allow us to fix any particular problem within the body, create components to fix and use whatever that might be. So certainly in terms of keyhole surgery, there could be some value that this could self-assemble once inside the body and within an environment that is automated. Externally, there's a potential to look at something like clothing. On one hand, perhaps when it rains, the material itself changes its structure, and therefore becomes harder, more protective, less absorbent, whatever it may be. Even to the point where perhaps we could have a hat, maybe it's something that when there is no appropriate change of shape, protection from the sun, or something like that. And a few of us seem to have a lack of hair, which is probably why we don't think about it. On the environmental side, the fact that the shape could be different depending on the ingredients that go into it. So perhaps there is things like deep sea oil, deep sea exploration, even like oil spills that seem to be introduced into environmental water to change shape and become absorbent, therefore absorb the oil, take it away from water. So it could be used in potentially sort of situations of natural disaster, which also led to a brief conversation about the energy that's within the system. We're having to input some energy. How much energy is needed for this shape to happen? And could we use the energy from natural disasters, for example, a tsunami, to help put the energy into systems and these structures to self-heal and therefore become protective to environments, to societies. So something on a much bigger scale that is driven by the environmental situation rather than by the specifics of the water. That was pretty much it.
Thank you. Next we have Sarah.
Hello, so I think you guys have had really good ideas. Our group just had a consensus about the social costs. So we figured that we have great ideas and projects that are happening in silos, and a lot of people, masses, don't realize that this is happening, and they think this is something else to happen. That's very futuristic. But the future is quite near, so we're talking about fully automatic vehicles and transportation, public transportation coming within the next 5 years. But people are not ready for that. What happens to the social costs associated with it? So we figured that there are three things that we were concerned about. One was that the cost. Is this something that many people can use? So all of the really interesting projects that we've heard from, can this be done in a small and compact way that everybody could be connected within, like micro farms?
something you have in the room? Or can this be easily understandable by people? The second thing we thought was really that we needed element of human in this discussion, which was about executive decision making. So, for example, with the cool robots that flying up to tall structures, could you have a point where they could flag up a problem, and that could go to an engineer who then examines it? And then, what about having those, for example, bus drivers? What happens when they're made redundant? Is there a skills program that we can all come together and create for them? Do we have to change our education system? Do we train for skills rather than careers? Or do we mix them both? Should we go to universities for degrees, or go to universities for every couple of years, for a few times, just to revise our skills? Employability, what happens to all the people who lose jobs? How do we get them back into working, because people will need jobs? So in the end, our idea was more about having a better ecosystem, where there is more transparency about interesting futuristic projects that are happening. Future that's really near, but people don't think it's that near. And having that ecosystem support competition and collaboration across companies to avoid monopolization of things that will affect a lot of people. And we need to prepare ourselves for that on a societal level. And the question for everybody else is this something the government needs to do? Do we trust them with this? Or is it something that as society needs to come together from a merger between the public and private sector? That's it.
Really fantastic piece of feedback. Next we've got Philip.
Hi everyone, I'm Phil Sage. I work for Hasbro, Toys and Games, and when you watch these presentations, it's very easy to kind of connect to your world and your complete 360 as you know it today. We have a lot of good ideas, but kind of stuck around the toy and game area because I think that's a really interesting kind of way where you can draw some of these conversations into. It's all about automation in smart materials. You can imagine a core toy and game which can potentially evolve over time. And the idea that you take a bit in a very basic form, and then it could be add a layer of learning, or you think about Transformers today, where it's a very complex toy and you pass it on to the parent, but then with this automation, allow it to transform, or maybe teach the child how to transform it. But also, it can't be a one-trick pony as well. If you give a toy or a game to a kid within the first 2-3 seconds, they either love it or hate it. They toss it aside, they play with it, and they love it and they cherish it. Could these, this automation, enable it or give it, second life or grow with the child? I think the idea of the toy that grows with the child is quite, it's a very fruitful proposition. We talked about Lego bricks as well. The idea of the Lego bricks which could self-construct, but then is that taking creativity away from the child? So there's two ways, that you could actually, interpret that. They're doing it now in Minecraft online, where you building digital construction stuff, and then pulling it all, back together to bare bricks and rebuilding again. But that creation is pretty solid in the digital world. How can you represent that in the physical world? Then we kind of switched away from toys and games, and we were thinking, right, okay, what about common core competency stuff around us, like cars? What I look at my car, it's full of scratches. Imagine you scratch it or bump it, and then as you kind of you're on the way home, it's self-repairing. Or the elements around you is somewhat kind of automated to your paint is perfect when you get back home overnight in the garage. And then we went on about space, and I think that's been touched on a few times. Eliminating danger and cost, the self-assembly up in the space station, for example, where modules can be sent up. So you're not spending billions on sending rockets up and sending astronauts, but the space station could be the enabler, and then you're building modules onto it. Again, self-construction. So that's where we ended up. So thanks very much.
responsive, rather than the sort of vision of future as this screen all the time with some sort of range in place. But all surfaces are responsive, and you can tell by the texture what that's trying to improve. The main concerns are the lack of flexibility of the sort of organic computing. Whether there's sufficient applications for that chain of something happens and you've got an immediate response, whether that actually is a problem, and then you can build up lots of continues together to form that kind of complexity, the same way with frameworks.
Yeah, we're talking about looking at how you can create common building blocks for self-assembly organic computers, and whether we would look at things like neurons as a basis for inspiration, how we actually make more complex self-assembly devices.
And then we'll talk about happiness for a long time, and the worries about how we can stop all this interesting relationships out.
Yeah, there were concerns around if you have self-assembly devices that don't necessarily have a lot of computing going on, how can you guarantee the safety in the environment?
Just a few more guys. We've got Ben and I.
Hi everyone, my name is Ali, this is Ben. Just to say we have the first three presentations were really great. Because I was fish memory, we went with Skyler because you were last and we wanted to focus in, so I think this is a lot on self-assembly. So well, hopefully we can add something to what other people have talked about. So we started by thinking about what applications could this lead to, what are the domains that this could progress into. And we came up with probably half a dozen, everything from things we've already heard about, and maybe self-healing, what about creating spare parts. And we decided to focus around two of those. One which might be a near-term achievable product, and one might be a bit more radical and more obstacles. And what I'm going to do is just give you a quick overview of those, and then Ben's going to try and put the pragmatism on that and say, here's some of the challenges and what are the things that you can do to try and overcome those. So the first one was again around the idea of furniture, IKEA, how you could create a flat pack that assembles itself. But then beyond that, how in context awareness, so if you have an IKEA sofa during the day, at night time, how can that morph into your bed or become another object depending on what your social context is within the house, and how you can make sure that materials that you code do that. Can that be extended to disasters as well? So if you have shelter requirements, can you just airdrop shelter materials in that self-assembly infrastructures that support the environment depending on what the context of the disaster was? So is that something that's achievable? It's almost a 3D printer killer, because the thing about printing with 3D printers is you need a 3D printer, but in a disaster zone, if you don't have it, you just drop something in that will allow you to do that. The second area, which was a bit more radical, was what's the progression about this, and if you want to take this to the moonshot, for example. So how do you take these ideas around fairly basic structures and formulating systems into creating really complex dynamic systems? So can you use the approach that evolution has taken with us as human beings, and use the idea of DNA, amino acids and proteins, and code materials with the knowledge to understand when you get put together in this combination is what you need to be. So on one hand, you can grow a phone if you want to grow an iPhone, or you can grow a school, or you can grow whatever you might need to grow. But it's how do you build that extra intelligence into the materials to understand how they're going to work, and the body is trying to produce those. So, Ben, how do you help with that?
I'm going to be really negative now. So we were looking at Skyler's examples, and they're mainly sort of geometric, crystalline analysis crystals. My background's in biology, so I kind of look at it from that point of view. If you take a sequence of amino acids, as you would have in a protein, you just dump them into water, it would misfold and you wouldn't get a functional protein. So actually what you have in biology is when the proteins being produced by the ribosome, you have chaperone proteins which help it to fold correctly. I think your chaperone proteins are kind of applying, reducing barriers to folding, so essentially applying energy in very precise ways, which is kind of what we do now in hand assembly. So I think maybe going forward to actually produce really complex systems, we need a hybrid approach between self-assembly and very precise application energy. In terms of complex systems, maybe synthetic biology is the answer here. So you embed all of the assembly information, all the complex sensing into the DNA of the bacteria, and then a more complex systems. I think if you were just to embed the information directly into the assembly materials, you wouldn't have able to include enough energy there. Enough information there to build a truly complex system. So I think that's what I think. Thanks very much.
Okay, we're down to our last three. Next we have Victor.
Okay, so we started really thinking about the public acceptance of and stuff, and then also figuring out how to actually make that accessible. Started working banging between the near future and today. Aside from making it accessible by thinking about something like a beer bomb that's self-cleaning, self-making, and self-serving. Really, all of the talks were really about this idea of a different way of thinking about how you build things, how you build systems that rejuvenate themselves. And really thinking about how that actually changes the education process that we start thinking about. It's about not learning a set of rules, but actually learning how to create sets of rules and not break those sets of rules and recreate things. That really came out of some of the discussion from our colleagues at our table who actually have engineering backgrounds and were talking about when they started learning, they were given a static set of finite rules. That this is a mechanical engineer, I know how this works, and I only work in this way. But the systems that you guys are creating are really about how you break that. And that very much changes the way in which we think about how we construct things, how we actually, we learn about ecology and ecosystems. We don't yet know how to actually build them ourselves. We're not actually teaching kids to actually work in that way. It's just learn this subject, learn this subject. How you combine those things is important to get to.
And now we walk.
Hello. So we were a table of men. So the first thing we did is we reviewed our previous presentation and we wanted to do robots. And then we kind of thought, well, that's a little bit obvious. So we went to address what was a bigger problem, one that a lot of people have been addressing today, which is about transportation and transport networks. And essentially it's really kind of mash up of what Skylar and Rachel did. And we've come up, our big idea is simply this: self-assembly organic roads. There's quite a few advertising people on our table as well, so we branded it as Good Roads. Trademark has been applied for. But the idea is simply this: is, and politics aside, there are, emerging countries, emerging areas. There is a need to move people and things around. So what we were thinking was, could you take dirt road and add a material that allows it to solidify? Perhaps a material that, if that road isn't used anymore, just simply melts away. And that material should be able to self-assemble. You simply just pour down at one end and it just puts itself together. And also, why can't that road actually help improve the environment? Is there a way that it could actually reduce carbon dioxide, take out other toxins that's existing? We know there's a lot of problems with that. But some of the things we took the ideas about, that anybody knows about baby incubator making Toyota parts, familiar parts, about using familiar parts, using local skills to actually do that, but also people, how do you involve people, and ideas like the kids roundabouts pump water. Could you actually get people doing normal activities in order to make all this kind of stuff work? We know there's a lot of politics, and we don't think it's our job to get involved with politics. So really what we've done is to come up with just this simple idea. There's a long way to go with it. As we said, this is a very long road, but we think this is a genuinely concrete idea. That was brought to you by Icons.
And last, we have a fantastic five led by Sylvan.
My name is Jamie, I'm a cycling journalist with Icons Media. Basically had a really good application for self-assembly. When you have a bicycle that's hard, you want it to roll quickly, you want it to grip as well. And you can't really have both those things at the same time, so it's sliding scale, you can't have one or the other. So we thought if you could do 4D printing, you create a tire made of two materials that adapted when it got wet to grow spikes, so they could slip water away. And then when you came into a corner, you needed that tire, either on a bike or on a car. It would become tackier, and it would change shape all the time, so the supporter, and give you greater grip. So
is created, it's spread across, they were in the central teams across the world. They basically worked in their environment, their ideas, came up with different uses of a material or something, like you said about the system that you could create and you could design. They would create their own designs, some of their own use, and then pull that data back to you. And then you could then see which one was the best one, and then start to think on that front. So this is from a material use perspective, multi-use perspective. Maybe something covered the use of tiles where it could be actually practically done, where you have a set of, say, one type of a role and then another type of role. So you could probably cover that as well. Still we cover, and we are quite fascinated with robots and
Yeah, I go back quickly as well and talk about the roadside here, and what struck my mind was the concept of today when planes landing, they has quality control. Basically, it's a random walk to desk flow with flashlight. And we thought about thinking about sort of more army robots that could actually go there with webcams and look more deeply in the structure and inspect really structural damages. And I think there's a range of idea around that quite exciting. Imagine the shark now, whether you like it or not, that's going to need some quality control and inspections and very difficult for you being a small army products going around. You go into simple that's all around the idea we have around the robots.
So the model essentially, you can think of this as a building. You can take 4 or 5 robots together, and then you can start connecting with each other, put data together, and get clean out of this. That's what essentially we thought could be used to do, and it could be done in various ways. Another person said that what if the requirement moves the guy over, whether you say the guy who comes on, what is what? He could be the job profile of the guy changes, and he could come in and actually analyze the data. And the data analysis could be used for you to say, okay, grade 1 risk, grade 2 risk, grade 3 risk, from an aeroplane perspective, from a building perspective, and that could help in deciding what material could be used, what is the risk factor of that aeroplane flying again, or a building condition, or a repair. So we feel that these two, I think, can be probably work together. Thank you so much.
So it was really nice to hear all of these ideas coming back around objects that grow naturally around human, around your body. That's something that we do. So we went from the idea of self-assembly into seeing the idea of growing your own organs as a type of self-assembly. And we started thinking about things like medical applications, what could self-assembly look like in that field. And we started thinking about what happens to self-assembly when that takes place inside one's body. That got us then to the idea of adaptive prosthetics. And what we did is we worked out sort of like a concrete use case, which we called an embrace.
So embrace is where the pearly whites meets perfect brace. So the brace that grows with you. So we came up with this idea that you could go to your dentist and you could get this new type of brace, and the brace will be kind of measured by the dentist. The dentist will set certain dates when you'll need to do something to kind of adapt the brace. So whilst you're using the brace, like after maybe the first month or something, will be like the time where you're reminded that you need to adapt things. So you can do like take a kind of drink and kind of just floss with it, and then it will reform to like the next notch that you need to kind of reform your teeth. And then like as you're going, like, we thought like maybe people might be a bit anxious about wearing something that's going to be adapting to how their teeth is adapting. So we had this idea that if it's too painful, it's too tight, or then the problem goes wrong, that maybe it could kind of vibrate in some way or give you a notification. So then maybe like it kind of vibrates and you think, okay, what's up with it? So you contact the dentist, and then the dentist says, okay, maybe there's something not quite wrong with it's maybe like an error one that we sent you out. So you can then reprint another one that the dentist sends the data to your 3D printer or 4D printer, and then you can kind of print a new one and then just carry on using it. And then at the very end, you can kind of take this magic solution which dissolves it and kind of gets rid of it. That was the idea.
Sensible things that have already been said, so that's really for a while. We took the approach of taking the actual context where we see a lot of problems and all these inventions feeds it to the plants, and maybe also taking the effort of breaking down the CO2 in O2 for us oxygen to breathe, and carbon, which we can compress to diamonds. And then we would have like diamond panels to construct a greenhouse with. I have to know the smiley face. So yeah, and then the robots could take over the construction and the maintenance of the greenhouses. So they could emerge everywhere where they find a suitable place for rising the greenhouse. And those little panels get growing inside of the tree. So yeah, we really construct this whole field with your inventions.
Big thank you to all of you. Apologies, we've run a little bit over time. I hope you all enjoyed this morning's session. For us, the conversation doesn't stop here. We'd really encourage all of you, if you have ideas, if you have more questions, to carry on the conversation with the speakers that presented today. And one final thing from me, we're running a hangout on air with this panel later on tonight. If you had any other questions that you wanted to join us for in this discussion, please come and find me. We'd love to speak more to you about it.